Welcome to CS1104 Computer Systems. This is the Unit 5 Lecture Part 1. During this lecture, we're going to cover the architecture of the computer. So up to this point, we've been talking a little bit about circuits and how they become gates, logic gates, and how we put those gates together to form functional areas of the computer system, such as the ALU, or the arithmetic logic unit, or the memory unit. What we'd like to look at today is a little bit of how it all gets put together and how we control what's going on within the computer. And so what we want to do is look at that from the architectural perspective. Now, the architecture that we're going to look at follows what we call the von Neumann architecture, or the definition of what a computer architecture is that was developed by John von Neumann. And essentially the whole idea that von Neumann came up with was this idea of stored programs. So the notion that the instructions that you're going to execute, along with the data against which you're going to execute, are going to be stored in memory, and that I can change that memory. I can change those instructions. I can load a different program, and in so doing, I get a flexible computing device. Now, up until this innovation by John von Neumann, most computing devices were very specific. They could do one kind of a task, and what the von Neumann architecture did was it created a new approach that allowed us to do a variety of different kinds of tasks, because I could change the instructions that were being executed. Now, some of the key elements of the whole von Neumann architecture is the idea that we've got a processing unit, or a central processing unit. And there's a couple of things that go on in that central processing unit. One of them we know about, which is the ALU. We've talked a little bit about registers. And then there's also this thing called the control unit. And basically the whole notion behind the control unit is that I have to have a way of coordinating what happens when. So the role of the control unit is that it keeps the clock. It's that element that has the clock that's ticking, and that clock drives the program counter, and the program counter is the thing that is defining which instruction we're going to execute next. So this is a very important part. We're going to look at exactly how this works in just a bit. Another element of it is this idea of the memory. We talked a little bit about RAM, and the fact that I keep RAM out separate as a large array that I can get access to, and the fact that I need to move that memory from where it's at in that memory array into the processor. Now, part of that's going to be executed by the control unit. We're going to look at that. But essentially what happens is I'm going to tend to move it out of memory. I'm going to move it into registers. And when it gets into those registers, I can then perform computations against it. Another element you have out there is the whole concept of I/O devices. That's not something that we're going to focus on in this course, but just keep in mind that it's out there. So we have I/O from an input perspective, perhaps from the keyboard, or from some other type of a device, your mouse, for example. Output might be, the screen or the printer, or output to a file. So I have a lot of different kinds of I/O devices. Now, another thing that we have out here that we need to kind of talk a little bit about is this idea of a signal. So we've been looking at everything we've been looking at for the most part in this course is around signals, and a signal is simply something that has a voltage on a wire. So everything we've been talking about, gates and switches and turning things on and off, are based upon this idea of signal, or the fact that there's the presence on a wire, a conductor of an electrical current, a voltage. And we obviously have two states. One of them is the voltage is on, and as we've talked about, we represent that by calling it a 1, and the voltage is off. We represent that by calling it a 0. And when we start looking at putting a series of these signals together, where I have multiple wires that come together to carry all of these different states, perhaps across what we're going to refer to as a series of bits, when I bring those wires together that carry the voltages, we refer to this as a bus. So a bus is nothing more than a group of wires carrying a voltage or not a voltage, a group of signals, and that grouping has a single purpose. And we're going to look at some of these buses in just a moment. So a couple of things we want to look at is that within our hack architecture, so all of what we've been leading up to is we have an ALU, what we're going to have from the perspective of our text is a ALU that's been designed around what they call the hack architecture. And essentially, it recognizes two kinds of instructions. Now, when I say an instruction, keep in mind what we're talking about here is a series of signals that are going to come across a wire. And in this case, I have 16 wires. That 16 wires represents a bus. And essentially what this is referring to is I have some memory unit out here. So in this case, it's going to be ROM, right? And that ROM is structured to have 16 1-bit memory cells that come together to form a word. And these words are organized into a long list forming the memory. Now we're calling it ROM, but it has essentially the same structure as the RAM. But I have these 16-bit words, and I can bring one of those 16-bit words, which is, when I say 16-bit words, it just means 16 bits, ones or zeros, on or off, and these form the instructions. And there are two kinds of instructions. One instruction has a 0 at the beginning of it. And what that 0 instruction is the remaining 15 bits provide an address. It basically just is referring to a location in memory, either the ROM memory or the RAM memory. So basically that's what the 0, or what we see in the book, is called the A instruction. And then I have the C instruction. The C instruction has a lot more information. Now, it begins with the 1, and the 1 indicates that it's a C instruction. Then I have an A. I'm going to talk a little bit about what this A does. But essentially what the A does is it helps me to select between two different groups of instructions that can actually be processed by the ALU. Then I have a group of 6 bits in here, which we call the computation. Essentially, these 6 bits are going to specify what computation the ALU is going to perform. So, is it going to do an AND? Is it going to do an addition? Is it going to do a subtraction? These 6 bits basically specify the computation. I have 3 bits following that specify a destination, and we're going to look at what that destination is. But think of it as basically being within the ALU. I have a couple of registers that come in. I have a register that comes out, and essentially this destination allows me to specify where stuff is going to go. And I can have things go to a register, I can have things go out to memory, and this 3 bits basically specify where I'm going to have it go. And we're going to look at exactly what these 3 bits are and what destinations they actually refer to. The last 3 bits specify jumps. Now, what a jump is it basically gives me an opportunity to define a branch in the code. So imagine I have some long program which represents these 16-bit instructions in my ROM, and I'm going to be going through them one at a time. So maybe this is the 0, 1, this is the 1, this is the second one, this is actually the third one, and the fourth one. And essentially, our system is going to execute these in sequence. It's going to start at 0, it's going to increment the counter to 1 and go to execute 1, and it's going to go to execute 2 and execute 3. Well, what happens if I want to go back and execute 0 again? The way that I do that is with a jump. And we'll talk a little bit about how this jump works. Now, the thing that we were just looking at, that C instruction with all of those bits on there, forms what we call a micro instruction. And like we said, it's formed up of these different components. It's got the computation piece of it, these 6 bits here. It has the destination piece of it, which is these 3 bits, and it has the jump piece of it, which is these 3 bits at the end. And each of these 3 areas has a very specific specification. So this table shows me all of the computations that I can do. It basically tells me what the bit pattern is of those 6 bits and what the ALU is actually going to process when I have them. So let me give you a great example. And by the way, I talked a little bit about the fact that this A here can have a value of 0 or 1, right? And depending upon whether its value is 0 or 1, it selects from 2 different groups of instructions. Well, let me show you what that means. On this side, we can see when that value is 0, when that bit has a 0 in it, these are the instructions that are executed when this bit pattern is present. So when the C bits have 1, 1, 1, 0, 1, 0 in them, and when the A bit is 0, then this particular instruction is executed. So it's going to pass to the out a -1. This side represents the instructions that are executed when A has a 1 in it. Now, all of this is important because one of the things you're going to have to do in this unit is take some code that we have, some assembler code, and translate it into binary. Now, when I say translate it into binary, you're going to have to take the instructions in assembler and figure out what these bit patterns are to actually execute that, or what the bit pattern for the 16-bit instruction, the C instruction and the A instruction, need to be to actually write the machine language code for that particular instruction. So again, when A is 0 or when A is 1, these instructions are executed. When A is 0, these instructions are executed. Now, when we look at the assembler, what you're going to find is that most of the instructions are going to take the form of like something like this. It's going to have something that might say M is equal to A plus 1. Now, let me tell you where the A plus 1 is coming from. When I say A plus 1, it's referring to an instruction that the ALU can perform. In this particular case, if I look over here, I can tell that this is the A plus 1. And I know that it has bit pattern of 1, 1, 0, 1, 1, 1. And I also know that it has to have the A bit being set to 0. So I know this is the instruction that it's going to perform. The equals M on this side is telling us where to put the result. And essentially, I have a number of different locations where I can actually pass the result to. And they are all defined by these destination bits up here. So we're talking about the fact that I can have these 3 bits that specify a destination. Now, the first one is I don't store the result anywhere. I just basically ignore it. But in this particular case, I'm saying I want it to be stored in M. So essentially, this would be M or memory. And essentially what it's doing is it's sending it to the memory register. And that would have a bit pattern of 0, 0, 1. So if I wanted to add 1 to the A register and then store it in M, right? First of all, I know my A bit is going to be equal to 0. My C bits are going to have the value of 1, 1, 0, 1, 1, 1, and my destination bits are going to be 0, 0, 1 because it's specifying M as a destination. Now you notice in some cases this is MD. That means it's going to send it to memory and to the D register. In some cases it's saying AM, which would mean that it's sending it, or the outcome of this instruction, the outcome of this computation is going to be sent to both the A register and the M register. Now what you're noticing here is that I have basically 3 different destinations that I can use. I have the A register, I have the D register, and I have the M register. And we're going to look at where those things come from in just a minute. Now I wanted to jump into, pun intended, the jump bits. And essentially, if you think about branching, this is that ability to go back somewhere in the code. And essentially what the CPU is going to do is it has something in there called the clock. And the clock just basically is something that ticks. Every fraction of a second, it might tick. And whenever it ticks, it causes the program counter to increment. What the program counter basically does is it's telling us which line of code to execute. So clock ticks, goes to the next program counter, the program counter then loads the next instruction into the ALU, and then it does the computation. Then the result is going to be stored in wherever we specify by the destination. Now, the jump basically gives me an ability to define under what cases and what conditions I might want to move to a different line within the code. And I have a number of different possibilities from a jump perspective. And essentially what all of them are saying is that I keep track of, or I should say the ALU keeps track of, the outcome of an operation. So whenever I do this calculation, right? Whenever I do this calculation, perhaps I'm sending the output to M, perhaps I'm sending the output to D, perhaps I'm sending it to A. But it doesn't matter. Whenever I do that calculation, the ALU is going to determine whether the output of this operation was something that was positive, negative, or 0. So if it was positive, negative, or 0, then I can take action on that. So for example, if I were to specify a jump, JGT, or jump if the output is something that is greater than 0, i.e. it's positive, that gives me an ability to control the flow of execution within my program. Now, if you ever think about assembler, think about the fact that how would I do a if-then-else type of a command? Because what that requires is for me to be able to do an evaluation. Maybe I want to say if, let's say I have a command such as if 4 is greater than 5. Well, you think about, how am I going to evaluate that? How do I do that in binary? Well, the simple fact is you can't. So the way that we actually evaluate that is I would say I'm going to put 4 into a register. Perhaps I'm going to put 4 into register A, right? And I'm going to put 5 into a register. So maybe I'm going to put it into register D, right? And I want to subtract these two. Okay? When I subtract them, I now know if 4 minus 5, okay, is negative 1, that means that this is not valid. So I can actually subtract things and then use the output of that to make a determinant. And that's how I actually evaluate things such as inequalities and equalities. And based upon the outcome of that operation, I can make a decision to jump somewhere. And essentially, that is how we do evaluations within assembler. Very, very important concept. So we got jump bits and the whole jump process, and the fact that this is how I do evaluations within assembler. I have my destination bits, so I'm going to say where the destination of the output is going to go as part of the binary, and I have my actual computation. Now, how does this get used? Now, let me just call out a few features of the architecture. The first one I wanted you to call your attention to, and by the way, some of these features I'm going to identify as being part of the control unit. Some of them are part of the ALU. Some of them are part of other elements of the architecture. The one I want to call out here is the relationship between the clock and the program counter. So the program counter is basically just a combinational logic circuit that allows me to count. It's an adder that adds 1 every time I tick it with the clock. And essentially the clock is just something that on a regular interval sends a signal to the program counter. So every time the clock sends a signal to the program counter, the program counter is going to increment by 1. And every time it increments by 1, it's essentially going to go out, and you notice I'm pointing to PC or program counter. It's going to send that number to the ROM memory, the instruction memory, because that number is going to be the address of the instruction I want to execute. So maybe it's going to send to this 5, right? The number 5, well, maybe in this particular case, the number 5 represents an instruction in the instruction ROM memory, and that instruction, because I provided the address, is now going to send the data out to be decoded and then sent into processing for the ALU. Now you notice I have this concept of a decoder here. You'll see that I have my jump bits down here, my destination bits here, and my computation bits here, and of course our A here. And remember, our A is going to specify if it's going to be the group of instructions on the left or the group of instructions on the right from the chart that we looked at here. So this is where that A bit comes in. Okay? So program counter sends the signal to which is the address over to the instruction memory. The instruction memory is going to load that instruction up here. That instruction is then going to be decoded. So we're going to look at the bits. And by the way, all these bits, essentially what we're going to do is we're going to just pass those wires directly into the ALU. That's going to tell the ALU what to compute. The other part of this is that what I'm computing. So essentially the ALU has the ability to do 2 computations. I can, and by the way, you notice here I've got memory, I have the A register up here, and I have the D register. So if you think about all of those destinations we had, essentially what happens is I can compute the A against the D, I can do the D against the M, because this mux is going to select between M and A. So I can do either A or M, right? And then I can do D. Now there's a few things that are unique here in how this happens. And one thing that we do need to talk about is the A instruction. And essentially what the A instruction is, it's a way of specifying either a value or a address as a destination. And when you think about the A instruction, essentially what that means is whenever I put an A instruction in assembler, it's going to automatically load into the A register. So just consider the fact that whenever I put the A instruction, which is specified with an @ sign and some number or a symbol, what's happening is it's just loading it directly into the A register. And essentially what then happens is once I've loaded my registers, A register, D register, and we know exactly how that works, right? Because we can see how we're specifying it back here. Let me see if I can find the right spot. Right, so we're basically telling it, and for this particular case, I want to execute an M-1, right? So in this particular case, it's going to be operating against the M register, which is this. It's going to be ignoring the D register, so it's going to essentially do a no op on it. It's not going to do anything with it to execute that instruction. Okay, I mentioned the fact that the jump is all based upon the idea that the ALU can determine the output of any operation as being negative, 0, or positive. And essentially what it does is it sets these bits up here. So I have the NZP, negative, 0, positive. And essentially, if it's negative, 0, or positive, I can test that and using and specifying the jump bits. Let me see if I find where I have that. Based upon that, it's going to take one of these actions. And again, this is how I actually evaluate things. This is how I can control execution of the code within assembler code. So again, the way it works, instruction is going to come in from the instruction memory. In our architecture, this is going to be ROM. Many computers, this is actually RAM, but a special area of RAM that's kind of segmented off for program instructions to sit. It's going to get into the decoder, and the signals, i.e. the wires, are going to be tied into the ALU. And all of these things, such as the multiplexers, etc., what they're just there for is to turn the switches on so that these signals wind up getting into the ALU. Obviously these destination bits are going to be sent out into the ALU, which is going to actually specify or turn on where this thing goes. So this output that we have here, you notice I have the output that comes in here. I have the output that's coming in here. I have the output that, where's the other one? But in every case, essentially what's going on here is that I'm just specifying where the output of this particular computation is going to go. Okay, so ALU, we know the operation of the ALU when I have things coming in. And by the way, this is a register and this is a register. So essentially these are memory structures that are going to hold state, and it's going to hold that state while the ALU is actually able to perform the computation, because the ALU is a combinational circuit as opposed to a sequential circuit. So it's going to perform the computation and be done with it. These registers hold the value while we perform the computation, and they're going to continue to hold it until the next clock tick goes on. And when the next clock tick occurs, then we're going to send a signal that will change the value in them to the next potential value. So this is giving us an idea of the control logic, the role of the decoder, because what the decoder is doing is bringing these signals, this instruction in, and it's allowing us to send the signals to the appropriate source. Okay, the one area we haven't really addressed a lot is this whole concept of RAM. Okay, and one of the things you notice I have coming out here is address M. So that A instruction One of the places that I can actually route it to is I could specify a memory address in there, and then when I route it, it will actually route it all the way over here to where this address M is. And this is how I'm actually able to read memory. You notice where it's sending is it's sending it out to the M, which basically is coming in here. And that represents the register for memory inbound. So again, we're down to those 3 registers. Memory register was bringing it out of the RAM and providing it into this MUX. I can have the A register, or I can have the D register. So you see all of the computations that we're performing are against A, D, or M. So you can see A here, D here, M here. Only A, D, and M are involved because I have to be able to perform computations using the registers. I think we covered the whole concept of the condition codes. And again, this is how within the architecture we can actually do branches, or we can evaluate expressions, because the only way that I can evaluate an expression is I can look at to determine if it is negative, 0, or positive, and then based upon that output, I can actually execute a jump. And when we get into looking at the actual assembler code, we'll look at that in a little bit more detail. So this gives you an overview of the architecture and how it functions, the whole idea of signals. And by the way, every time I have one of these little bubbles here, essentially what we're referring to is that this is some signal that's coming in. And I just use the bubbles to connect them together because, quite frankly, there'd be so many lines going around here trying to define the different flows that it would be almost impossible to read. I urge you to kind of study this picture because it'll give you a good sense of how the information is flowing through the computer architecture between the RAM pieces, between the memory or the ROM pieces that we have here, the registers, the control elements here, which is the clock, the program counter, the decoder capabilities, okay, and the ALU. Now, one other point to keep in mind, everywhere you see one of these blue lines, essentially it represents a bundle of wires capable of moving that 15 or 16-bit instruction or word of memory. So every one of these lines represents essentially a bus. So this is our overview of computer architecture, and in the next unit we're going to take all that architecture, we're going to learn how to apply it with assembler language to actually start writing programs against this computer architecture, most of which we've actually designed.